Okay, so we've reached now a point in 7.5, or sorry, in chapter 7, where we really have seen a grand variety of strategies with integrals of a specific form. But now it's time to collect and overview our strategies for, or our techniques for integration in a way that, sorry, maybe this is why I should talk and say the same thing that I'm writing. Right, so now it's time to talk about like what our, critical thinking process should go through as we encounter integrals. And so we're going to do a variety of integrals here. And then we'll see how they kind of all work together, where to start, what to do when some of the techniques fail us, and just go from there. So first, I'd like to just go ahead and talk about like what is exactly our toolbox, like where to start. So the first things that kind of is the, it's like the go-to thing that pretty much everyone is going to start with within integral is just simplify as much as possible. Okay, so wherever possible, simplify the integrand, and hopefully maybe you can use some identities, right? Like if you have a trig function involved, some, algebra that will make the integrand a little bit less complicated and convoluted. And that really kind of runs the gamut. There's other things that we could conceivably look at, but that's kind of beyond the scope of our course here. But just look at the integrand, see if it's maybe written in a more complicated fashion than it is, and then that'll tell you where to go from there. Our second thing that we should look at is it a basic rule? So basically, we have a table of integrals, a standard table of integrals, where we have like so we have like the basic trig rules, we have the power rule, we've got things like the inverse trig rules, got your logarithm rules, exponential rules, and so on, right? So there's like a list of 20 or so integrals that we know how to handle if you encounter, for instance, the integral of tangent of x dx, right? And that sounds obvious, like, okay, we should know that that's where we want to go. But sometimes you don't see that until you start simplifying. The other thing is maybe there's an integration by parts that needs to be used. And it's not always, clear, right? Because integration by parts can happen with a single integrand or with a product of integrands. And typically you see this if there's a product, but not always. Sometimes, if the integrand is something that you literally cannot integrate directly, then it's helpful to do integration by parts. Okay. Then you can run through your other techniques, like techniques for trig integrals. If you have a trig integral, in the case where you have something where you have, a square root, then you may need to use a trigonometric substitution. And we'll see an example of that where we, it isn't obvious that we would need to use it, but we would use it. Okay. Then, what else can we use? Long division, right? That's kind of attached to simplifying, but that lends itself to maybe we need partial fraction decomposition. And so you remember there's several flavors of that, and we know. The other thing is we might have to rationalize the integrand. And if none of that works, then there's a few more things we can still use. You can use a table of integrals. That's the subject of the next section. A table of integrals is a book, or a short document that contains basically a bunch of different general integrals, and you can kind of play around with them and see which one will work. You could also use a computer algebra system. And again, we'll get into this later, but this means software, really. It's software that helps you perform symbolic integration. We'll get into all that later. And then, if none of this works, maybe we can't integrate it. Okay, that sounds ominous, but let's just briefly talk about that, because I think it's worth discussing. So, we should talk about elementary functions and non-elementary functions. So all the integrals that we've worked with so far, even the really complicated ones, they can be expressed as a combination of elementary functions. So basically, those are all the function families that we've discussed since the beginning of Calc 1, right? So we're talking about your algebraic functions, right? We've got your root functions, got your polynomial functions, got your rational functions, right? So that's the broad category of that kind of functions, right? And you know that rational is a fairly big category, and polynomials is a subcategory of that, and so on, right? There's also, you've got your transcendental functions. You've got your trig functions, got your inverse trig, you got your exponentials, you got your logarithmics. So these are kind of in their own world, but those are all what we call transcendental. There are functions that live beyond this, though, okay? And we can't represent them as elementary functions because, by definition, they're not, okay? So here's an example, okay? So this is kind of a prelude to an application that we're going to see in Chapter 8. But if you've taken statistics or are vaguely familiar, we say a random variable, z, capital Z, has the standard normal distribution which is also written curly n 0, 1, if the probability density curve for the function looks like a bell shape, centered at 0, and with a standard deviation of 1. So what this curve is, which we're going to call lowercase phi of x, it's 1 over, is it this square root of 2 pi? Yeah. 1 over the square root of 2 pi e to the negative 1 over x squared. And this function is elementary, but its integral from any piece, right? So if we want to find a probability associated with this random variable, say for instance from 0 to 1, we wanted to find the area under that curve, we would need to use, so for instance, the integral from 0 to 1, phi of x dx. So by definition, the probability that a random outcome from this distribution lands between 0 and 1. Think of it like on a dartboard, right? And this cannot be expressed as in terms of an elementary function. In fact, we just kind of call it, we would use this new function called capital phi of 1 minus capital phi of 0, and this capital phi can't be expressed in terms of elementary functions. It can only be expressed as an integral. And for that reason, we use technology and tables and all that to actually write down values of this function. All of this is to say that this function, when we try to integrate it in any form, we cannot find a standard antiderivative for it. It's just not possible. So it's not an elementary function, and for that reason we need other techniques, including ones that we're going to cover in a later set of videos, including approximate integration and computer algebra systems. Right. So that's enough for this video.